Hi, the lecture today is about how to sketch a curve. I'm going to go ahead and list the basic topics that are involved in this section and give a brief explanation of each. In this lecture I'm not going to do any specific examples. I'll just list the topics that are related. Curve sketching requires all the knowledge that you have gained since Algebra 1 all the way through Calculus. As such, it is both very interesting and also challenging. Let's see what is involved here. The very first thing that you go through for sketching a curve is point plotting. Point plotting is just finding the coordinates of various points on the curve and connecting them and hoping that is the close approximation to the actual picture. Calculus teaches us how to improve our picture and validate our guesses. So we need to know about the domain of our curve, about the range, its intercepts, symmetry, tails and asymptotes, first derivative analysis, and the second derivative analysis. Now I go ahead and explain each of these items. In the point plotting, as I mentioned, you just find the coordinates of several points and connect them, and that's going to be a good starting guess. We always have in the back of our mind that such an approach always has the risk of missing important features on the picture or creating a wrong impression. So we go ahead and try to improve our picture by going through the remaining topics in this lecture. The domain of a function is the first thing we pay attention to. That's the set of all the x's for which the value of y is a real number. Real number means that we are staying away from infinities or complex numbers. There are a set of standard things to watch out for. The very first one is that if you have a square root or even root, you have to make sure that your radicand is larger than or equal to 0. Otherwise you'll be ending up dealing with the complex numbers. So the solution of this inequality is going to give the domain of the picture for you. If you have a fraction with a numerator and denominator, you have to make sure the denominator is not 0. The solution of this inequality is going to give you the domain. We have some other items too that sometimes we come across them. If you have your function includes a logarithm of an expression, then that expression has to be larger than 0, otherwise logarithm is not defined. For the trig functions, you remember that occasionally you have a hidden denominator. For example, tangent is really ratio of sine over cosine, and if cosine becomes 0, then tangent becomes undefined. At what angles does it happen? And that angle is either pi over 2 or minus pi over 2 or any of these other numbers. The story of tangent and secant in that respect are similar. Also, cotangent and cosecant, they have a hidden denominator. They have a sign of an expression in the denominator, and that angle has to stay away from 0, plus or minus pi, plus or minus 2 pi, and so on, for your expression to be defined. Less common, sometimes you come across the hyperbolic function. Cotangent hyperbolic and cosecant hyperbolic have a sign in the denominator, and that becomes 0 when the expression is 0. You want to avoid that. In order of importance, these two first items are the items that you come across more often. Every now and then you encounter logarithm, and then tangent every now and then is seen. The rest of these probably you don't see all that often. How about the range? The range of a function is the set of all the y values that you get. If you take the graph of a function and crush it on the y-axis, whatever is left of it is called the range of that function. Finding range is actually a complicated task. You have a couple of tools in your tool bag for finding the range, and typically you need to go through the whole problem first and then come back and figure out what the range was. Of elementary tools that you have available to you is that you know that the range of a function is same as domain of its inverse function. Go back to the lecture on inverse functions for an explanation of that. Second item is that if you have a function that is continuous and achieves its maximum and minimum, absolute max and min, then the range of the function is going to be going from absolute min to absolute max. One item to pay attention to is that if your function has a horizontal asymptote and the graph does not intersect its horizontal asymptote, then you have to make sure that you exclude the value of the horizontal asymptote from your range. We come across some of these in examples to be seen later on, so just keep that in mind for future use. Next item that you need to know about the graph are its intercepts. A graph typically has several curves and lines in it. Intersection of any two of them will be of interest to us, and we have special names for some of them. The ones that you are most familiar with are x-intercept and the y-intercept. To find the x-intercept, you set your function of y equal to 0. You typically solve an equation and you get an x value. For y-intercept, typically your task is easier. You simply plug x equal to 0 and find the value of y, and this activity is going to give you just 2 points of the picture. Somewhat more complicated is the issue of finding asymptote intercept. Sometimes your function cuts through its asymptote, and that crossing point becomes an important issue for us. How do we find it? Well, first of all, you need to know where the asymptote itself is. For suppose you have this horizontal asymptote at y equal to L, and you want to know where does your function cross it, if it crosses it at all. In that case, you take the function f of x, set it equal to equation of your asymptote, the right hand side of it, solve that, and then you get location of the crossing point. So f of x equal to L is an equation whose solution is going to give you asymptote intercept. Somewhat more interesting, a bit more challenging also, is the slant asymptote intercept. You might have a function that perhaps has a slant asymptote, and perhaps the two of them cross path. How do we find out at what point that happens? Well, again, you need to know where your slant asymptote is. You need to have the graph of the equation of your function, and all you have to do is solve a simple equation that description of the function here, f of x, has to be same as the description of your slant asymptote. You set them equal to each other and solve it, and that gives you the location of the crossover point. Now, how about crossing your vertical asymptote? Well, a typical function doesn't cross its vertical asymptote. If it did, it's going to violate the vertical line test. So for that technicality, you don't see this thing, but if you just have an equation and the equation has an asymptote, this is quite possible. So the only reason we don't mention the vertical asymptote intercept is that our functions are actually functions, and that doesn't happen for a function. So more interesting and more challenging than all of these things is the issue of a self-intercept. You haven't seen an example of that in the course yet, and probably have to wait for Calculus 2 to see an example of this. A function, graph of certain equation could have the property of cutting itself. Again, it doesn't happen for a function, but it could happen in other circumstances, and finding such locations is a task all by itself. I wouldn't say much more about it now. Now we come to the issue of symmetry. Knowing about symmetry is very helpful in graphing and understanding what's going on. And you have learned about a couple of symmetries in your courses, perhaps college algebra courses. I quickly mention them, and then we are going to move on. One type of symmetry is symmetry with respect to y-axis. That means your picture can be folded across the y-axis, and that is going to give you another picture which is identical to what you had to begin with. If this was a page and I was folding it on the y-axis, the right and left side would coincide on top of each other. How can we tell a picture will have this property before we draw it? If you have a function and you replace the x of it by minus x, and the resulting expression is same as the original expression, we say that we have symmetry. Such functions are called even functions, and sometimes we say we have axial symmetry. There's another kind of symmetry you come across, is called central symmetry. Here's a typical picture. The way to know that if such a thing is happening or not is to replace your x by minus x in the function. If f of minus x becomes minus f of x, you know that you have an odd function and you have central symmetry. For any point on the graph, there is another point in the opposite quadrant with the coordinates being exactly the negative of the coordinates of the first point. That occasionally happens. We need to know about it. Another kind of symmetry that you come across is so-called translation symmetry. Sometimes a function has a property that it repeats itself over and over again. Such functions are called periodic function, and they have a period. Period is the length of time you have to wait until everything repeats itself again. These functions can be detected by having a number p such that if you replace x by x plus p, the function does not change at all. You know that trig functions have this property: sine, cosine, cosecant, and secant. All of them have period 2 pi. Tangent and cotangent have period pi. But a function could be a lot more complicated than any of these and still be periodic, like a typical heartbeat. Next item we are going to take a look at is the issue of asymptotes. We have a lot to say about this because all sorts of functions have their own asymptotes, and we need to be aware of it. The general idea of asymptote is that you have a complicated function that you want to study, and you want to simplify it. If the simple function and the complicated one come very close to each other, far away from the origin, you say that you have an asymptote. Well, in calculus, first you learn about linear asymptote, that is, lines that come very close to your function. There are 3 types of asymptotes you see. First type is called the horizontal asymptote, abbreviating it as HA. So right horizontal asymptote happens when the limit of a function as x goes to infinity becomes a certain real number, say L. In that case, you say that you have a straight line and the graph of your function comes close to it, far to the right. If you take a limit as x goes to minus infinity, then you have a left horizontal asymptote. In this case, the function comes close to a horizontal line far to the left. One thing you need to pay attention to is that you need to determine if the graph stays above, below, or does it crisscross its horizontal asymptote. Easiest way to check that is by testing several points far away from the origin and figuring out for yourself which of the cases it might be. There are of course more rigorous ways of doing the same thing by using inequalities. Let's just quickly take a look at horizontal asymptotes for a variety of functions we have seen. For the rational functions, which is a ratio of 2 polynomials, if the degree of the numerator is less than the degree of denominator, then x-axis, that is y equal to 0, is the horizontal asymptote. If the degrees are same, if they match each other, then you take the leading coefficients and divide them, and y equal to that ratio is your horizontal asymptote. So that's a quick way of finding the horizontal asymptote. For exponential functions, remember, exponential function by itself has a left horizontal asymptote right on the x-axis itself. E to the power of minus x has a right horizontal asymptote on the x-axis. For the trig functions themselves don't have horizontal asymptote, but the inverse trig functions do, and the issue is rather complicated. let's just pay attention to at least one of them. Tangent inverse of x has a graph looking like this. Tangent inverse of a very large number is about pi over 2 or 90 degrees, and a large negative number, tangent inverse, is going to be minus 90 degrees or minus pi over 2. So tangent inverse has two horizontal asymptotes. Left and right are different from each other, and the picture looks like this. Less common than tangent inverse is cotangent inverse, and the picture of that looks like this. The right horizontal asymptote is right on the x-axis, and on the left its asymptote is at pi. For secant inverse, the picture looks like this. So you have two asymptotes, one on the right, pi over 2. The one at the left depends on the text that you read. For our current text, for most of the cases, for the formulas, they take this definition. So there's a horizontal asymptote at this location. Cosecant inverse, a similar picture to that. We have two horizontal asymptotes on the right and left. And so you study these pictures in case you come across them, but chances are you don't see them all that often. For the hyperbolic functions, remember that tangent hyperbolic of x does have a horizontal asymptote at 1 and minus 1. So the right and left are again different. And similarly for cotangent hyperbolic, picture is somewhat like this. Again, it's quite rare that you actually deal with cotangent hyperbolic, but every now and then maybe you see the tangent hyperbolic of x. Secant hyperbolic, x-axis itself is the horizontal asymptote. Similarly for cosecant hyperbolic of x. Let's go to vertical asymptotes. Vertical asymptote happen where the limit of a function as you approach to a certain point, either from right or left or both ways, is either plus or minus infinity. If that happens, then we say x equal to that limiting value is the vertical asymptote. Here are the recipes to remember for figuring out the vertical asymptotes. For polynomial, the process is very simple. You first simplify and cancel common factors, set the denominator equal to 0 and solve that. The solution is going to give you location of vertical asymptotes. Somewhat less common than this, every now and then you come across logarithm. You remember logarithm of x itself has a vertical asymptote right on the y-axis. In general, you set the argument of logarithm equal to 0, solve that, and that's the location of the vertical asymptote. Also remember for all the trig functions with a denominator or a hidden denominator, you can have a vertical asymptote. For example, tangent has a cosine in the denominator. Whenever cosine becomes 0, you have a vertical asymptote. Well, these are the angles at which that's going to happen. Similarly, for cotangent, you can have a vertical asymptote at 0, plus or minus pi, and so on. Slant asymptote, in this course you only see slant asymptote for rational functions, ratio of two polynomials, and the recipe for finding a slant asymptote is straightforward. Take your fraction and actually perform a long division or a synthetic division, whichever you like. You are going to get a quotient and a remainder. This quotient is like the whole part that's going to give you the asymptote. If it's a straight line, you have a linear slant asymptote, and that is going to play a role in drawing a graph for you. And even if it's not a straight line, that's still very useful for graphing the function. You get a nonlinear asymptote in that case. Next, let's go to the first derivative analysis. That is where the bulk of application of calculus comes in. You remember what the critical points were. These are the points inside the domain of the function where the derivative either 0 or the derivative does not exist. First you find them. Then you make a sign chart. sign chart. The first line is for the x-axis, next line is for the derivative, and the third line is your verdict about the function. Wherever the derivative is positive, you have an interval of increase. Derivative negative, you have an interval of decrease. You use these things to find the relative maximum and minimums. So if you have a critical point C, at the point at which the derivative either becomes 0 or undefined, and you check the derivative sign and it goes from positive to negative, means you have been going up and then down, and you have a relative maximum at that point. If the opposite happens, derivative is negative first and then positive, you have a minimum at that point. These two pictures are the more common pictures you see. These are where the derivative had become 0. Occasionally you come across situations where the derivative becomes infinity. In that case, you have a cusp at these points. Other possibilities also exist. For example, your function might just fail to have a derivative without having infinite derivative. In that case, you'll have a sharp corner. For example, the function might go up simply and then just come down. It's not a cusp, and it's not a smooth curve either, but it is a point of relative maximum. Similarly, this could happen at the other end as well. Again, these are rather uncommon occurrences for you. Every now and then you have a critical point and the derivative stays positive before and after. What does that mean? It means the function perhaps became flat and kept increasing, or perhaps if the derivative was negative on both sides of critical point, the function just stayed flat and kept decreasing. These two pictures happen when the derivative at the critical point is 0 and the sign does not switch. What if the derivative was infinite? In that case, you have a function that comes at this point and has a vertical tangent line. Okay, at this point, every now and then you become interested in vertical tangent lines instead of horizontal ones. Here is a vertical tangent line. Again, here is in a situation where you have a vertical tangent line. So you can just be aware of that. When the derivative is infinite and at both sides the sign of the derivative is the same, you have to compare the picture here to the picture that we had over here. It is here the derivative becomes infinite, but the sign of derivative flips. In the picture that I just had down here, the sign did not change. Finally, for a given picture, you have to go through a second derivative analysis. You have to calculate the second derivative and do a sign chart for that. If the second derivative is positive, in that region you have a graph that is concave up. If a second derivative is negative, you have a function that is concave down. If the behavior flips from one to the other, either way, from concave down to up or from concave up to down, the point that separates these two behaviors is called the inflection point. So you need to be aware of the 4 possibilities when you combine the first and second derivative analysis together and you want to draw your picture. These things become important for graphing complicated function. If first derivative is negative and second derivative is positive, means the function is falling down but it's concave up. Picture looks like this. If both of these are positive, the function looks like this curve. If the first derivative is negative and second derivative also negative, the function here falling down and it's also concave down. Here first derivative is positive, which means it's increasing. Second derivative is negative, which means it is concave down, and that is going to be how the function appears in that section. These were the main points of graphing of a function. Now we actually need to go ahead and graph several functions and see how do we put all of these things to good use. I recommend that you try to solve at least 10 problems from this section, and also attend all the classes and see how graphing gets to be done. Good luck and God bless.